Okay, this week we'll talk about regression diagnostics. Um, we actually have mentioned that um, being building a valid model is really important. Um, so that's why we are going to do some of the diagnostic work for the regression model we built to make sure it's all the assumptions are valid and the model is built the right way. Remember that we have been assuming the simple linear regression model was valid for the data. That is to say, we have been assuming the expectation of this y given x equal to the small x is this is a straight line. In mathematics, it's just beta 0 plus beta 1 times x. And also, we assume the variance of the y when x is given, it's the sigma square. So how do we decide whether the model is valid? That's the topic for this week. And what happens when the assumptions are validated? For example, it's not really a linear line, or the error do not have equal variance. Those are part of our assumptions, right? And what should be done in response if we find something is invalid or some of the assumptions are not met. Okay, so this is our target questions. Next is called a tale of 4 datasets. If you have not heard of this, it's actually example created by this person and to showing you if you are not really careful enough, only looking at the data by itself, it can give you really misleading conclusions. So I'm showing you here what the data looks like. We have 4 different predictors and 4 different responses. And we will first do a summary of those X's and Y's. And if you look closely, all these X's, they have the same mean. And all the Y's have the same mean. And what we're going to do here is we regress y1 on x1, y2 on x2, etc. for y4 on x4. Yeah, so by the first glance, you find, okay, they have the same mean, which probably means they are very similar data, and y have the same mean, and by looking at these numbers, you might have some of your assumptions built. What if we built a regression model for each of these 4 data sets? By looking at the summary of well, this is a bit busy. Let's just start from the left-hand side. This is your regression model. When you do a summary, you will see this. It shows you like the, well, by the way, sorry, this is the ANOVA table. Well, it gives you the similar information, but let's just look at this p-value here. And this f value is doing a different kind of test, but you have this f statistics and you have this p-value listed. And if you just look at the statistic value and also the p-value, oh, you can tell they are all significant. And by looking at the linear regression, the estimates, least square estimates, and they are all very similar, right? For the 4 different data sets, 4 different simple linear models. And the coefficients for the t-value and the corresponding p-value for the test, intercepts and slopes, very similar results, right? If you only look at here, they are basically have the same model, and they all look good because the p-values, they're all significant. But if you plot the data, it tells you the true story. So for the first one, it looks okay, right? And for the second one, the data is not really a linear. It's not really a linear relationship. And for the third, there is an outlier kind of data points. And for the fourth data set, well, this data point kind of controls the whole line. So this one is not linear relationship, and this one outlier data, we may need to taking a look at it. And this point is creating the whole model. Basically, this is the mean of this group of data points, and like if this data point is over here, then the line would be something like this. So this one basically determined where the line is. So overall, this one is okay, but this three are not okay. Yeah, so, well, I showed you they all have the same kind of summary statistics, but when you plot it, it tells you the true story, right? So in this case, well, by just looking at the scatter plot, just plot your data, it will tell you if the model you built is valid or not, if it's appropriate or not. But for this case, all this 4 data set, they only have one predictor variable for each data set. So that's why you can do this kind of checking one by one and look at the relationship between Y and X. What if you have multiple, you have more than one? So the first tool for diagnosis for a regression model, no matter it's for a simple linear model where you have only one X, one Y, or for multiple linear regression where you could have multiple X. But in that case, it's hard to plot all. For example, you have 6 different predictors, 6X, and you plot Y versus all 6 of them, which is not really easy to look at, right? It will be messy. So in that case, making a simple like scatter plot may not be a proper case for checking. So the first tool we are going to talk about for the diagnostic is to look at the residuals of your model. So what is the residuals, if you remember? Residuals are the difference between the actual value of Y and the fitted value of Y, which is fitted value in Y hat. So EI is the residuals equal to YI minus the fitted value YI hat. Plotting the residuals against X values, it will allow you access visually assess whether a appropriate model has been fit, no matter how many variables you have. So it works for both our current case simple linear regression model, and also like in the future we'll talk about multiple linear regression. This is a tool that can be used on both, beside the scatter plot. Okay, so why does a pattern to the schedules tell us something about the whole model? Or if we look at the math, suppose the true model is a straight line, as we always been assuming. This part is a straight line being beta 0 plus beta 1 times xi. And then assuming our estimates is good and beta I is close to beta I hat, or I should put the other way, beta I hat is close to beta I, because this one is estimated and this is the true value. Or anyway, these two are close. So when you take the residuals, you write them out. It's just like this, right? Beta 0 minus beta 1, beta 0 hat plus this difference times xi plus ei. And if they are close, this should approximately close to the true residual ei. And so in this case, our residuals resemble random errors. So we just check the pattern of the residuals to check if it's really look like random errors. Random is the key word here. If the residuals vary with x, which means have a relationship with x, residuals show some pattern, some relationship with x, then that's a marker of an incorrect model. So that means it's not like fully random. The residuals are not fully random. Then it indicates an incorrect model. Suppose the true model of the data is a quadratic model where you have this term like xi squared, which is a quadratic term, and we fit a straight line regression on it. Then we get, so again, we have like close estimated beta 0 hat and beta 1 hat. And when we calculate the residual, it looks like this. But we have this extra quadratic term because in the straight line case, we only have this first two term, right? For like with this yi hat being beta 0 hat plus beta 1 hat times x, that's our yi hat because we're fitting a straight line. So when you take the difference, then this quantity is left out with our true residuals. So this will show up as a pattern in the residuals that resemble a quadratic function of x. So that's from this part. So this is how the pattern, like a raw model, will show up when we plot the residuals. Take a look at the example that we just talked about the 4 data sets. Well, the quadratic nature of the data is apparent from a scatter plot that we saw before. Well, this example is designed to be simple. We can also come to the same conclusion from the following residual plot. So this is when you plot the data, the scatter plot for y2 and x2 shows clearly a quadratic pattern. And when you calculate the residuals and plot it, the quadratic pattern is reserved in the residuals. So in this case, it's clearly showing a pattern, like the residual have a relationship with this x2, which means it's not really a random residual. Like it's not showing like a random pattern. Random means it can go anywhere, but not with this curve pattern. Okay, so this is an example of being checking the residual and find is not a valid model. Well, the general pattern of a diagnostic regression model, it determines if the proposed model is valid, typically through plots of standardized residuals. And also it determines which data points have X values that have a large effect on the estimated models, which is called leverage points. So this is something we're going to talk about next. But here I'm just showing you like the general rules or general steps to do the diagnostic for our model, so that you have a picture why we're talking about those like in the following sections. And also we need to determine which data points are outliers. That is to say, do not follow the pattern of the rest of the data. That's the outlier. And see, we need to find this leverage point. If a leverage points exist, we determine if they are bad leverage or If they're bad, determine their influence on the fit. So leverage points, outliers, determine if leverage points are good or bad. Also, we need to examine if the assumption of the constant variance of the error is reasonable or not. So we'll look at the variance of the errors. If the data are collected over time, examine if the data are correlated over time. So that's an extra step if you have time series data. Which if the data is correlated with over time, then that means it's not random. You need to take extra care for it. For small sample sizes, or if you want to prediction intervals, examine if the assumption that the errors are normally distributed is reasonable. So we know by large number theory, we know when the data size is large, data will approximately follow normal distribution. But if your data size is small, then you would want to check if your data is really, if the error of after the fitted model, are they really normally distributed? So that's another thing you need to pay attention when you have small sample size. So this is general rules or steps to do the diagnostic. So next, I'll repeat this again, but for now, we'll talk about the leverage points.